Welcome back, everyone, and this is the final video of our King's Kai project. So I just want to quickly show you some pictures I was using as a reference. So here's King's Kai planet as a whole, and zoomed in, or another shot from the cartoon series. This is what the house kind of looks like, and they had a little water fountain and a garage and some trees. So these are my source picks, and finally the product came out like this. It's not beautiful. It's kind of ugly, in my opinion, but it captures the overall shape and idea of what King's Kai's planet is supposed to be. You got that, and that. You got the house, you got the garage. I didn't build the bench because I think the zoomed in picture does. Oh, it does have the bench, but whatever. I didn't feel like making a bench. And you got the water fountain thing. I just didn't put that little sprout. But yeah, we can. Let's see. Can we zoom in? You can zoom in. And I don't know why this needs to start. But yeah, here we are. We're at King's Kai's castle. We need better camera controls so you can kind of walk around the planet. But yeah, there you go. And I'm not really gonna go through the step of really just completing the planet, because I made a video about the trees, about how making the road, how to make the planet. The rest, like the house, the garage, and that, it really follows the same thing. It's just me plotting a bunch of points and either using a lathe or an extruding function to kind of just extending it and then doing a triangle thing on it. So pretty much all the functionality, the build, the main three parts, the road, planet, and trees, were reused to really just build the rest. And it's just being creative where you put the points and using the functionality. The only small difference I did was, I know when it comes to the house and the fountain, I had that fourth component. And the fourth component, I would just put like a color index. So this way I can color each vertice differently. So this way the house, other than the door is actually a separate mesh, kind of just wedged in there. But the house, all these points have one color. Those points have white. That has another color, another color. So I just used the fourth component, and it just had a shader built for it. I'll quickly show you the shader. But yeah, this is King's Kai's planet. There's a couple other small bits of functionality I'm just going to quickly go through that we upgraded to the core, and other things that you might want to use. So if we go back, the only big difference I did to the core is I updated material. It has some functionality that's been missing for a very long time. One thing, there was like a third parameter here, I think called OPT, options. I took that out because I'm not using it. I just had it there as a placeholder. But what I really did with materials is I added set uniform and apply uniform. So I'm trying to think. I'm trying to remember, do I do the same thing with the shader? I think probably the shader too. Not the shader, whatever. So originally materials, we couldn't apply uniforms to it, so all the shaders had to be hard coded. Now we can actually set up some, so we can. So I was able, because I needed to have the same shader, but I need to apply different colors that based on the model. So I end up creating multiple materials using the same shader, and to be able to push custom uniforms per call, I need to be able to save uniforms. So this is now, it actually works like a real material kind of object. So set uniforms is when you just like the way we've been doing it is just add as many parameters as you want, and as a key value pair, and then it'll just loop through arguments and then save it to a local array. And then down the line, when we render, we just apply uniforms. So I think the other big change is really at the end. It's where our renderer Right at the very bottom is our nice little renderer class. And I believe when we do prepare next, so while we're preparing our materials, when we're all said and done, we apply uniforms, and that's it. Now we have custom uniforms that we can create multiple materials. So that's all I did to the core. Just some two new functions, and a little upgrade to the renderer so we can use the apply function. So let me go to the Kai's file. I threw all the functionality related to creating the planet in this one file. Everything from creating the tree and everything else. Pretty much everything is the same. Everything in the Kai namespace hasn't changed at all. What I do have is a couple of new functions. I have an Eclipse, and the Eclipse function basically all it just gives me an array of points. Because I wanted to create the house not in a perfect circle shape, more of an ellipse shape, like of an oval. And the only big difference between a circle and an ellipse is that you add a second radius. So I think I might have had a circle function before, all you had to do is just I think you just pass in one radius. In this case, you pass in two radius. That's really the gist of it. And I think this one, I picked the starting and the ending angle. So instead of making a complete circle, I can actually start at any angle and end it in an angle. So this way I was able to make like a half circle or a half oval type of shape. So that's all it takes to create an ellipse path. And that's all it is. And C is for color. Because like I said, I was using the fourth component to color things. So this is like kind of a custom ellipse function. Ideally, if you're going to use this, you probably take away the C part because you really don't need it when you're using your own stuff. But yeah, that's one function. There's other functions in here like that added house, door, garage, fountain. I'm really not going to go to explain every single one because like I said, they're the same thing. Like I said, I'm using the ellipse, and then I'm just kind of extruding and triangle walls. It's basically the same thing we've done on other lessons. So it's kind of rinse and repeat with just different paths. So that's what house, door, garage, fountain does. Sometimes like a fountain was kind of like a trial and error type of thing. Like I said, if you're really curious on how I build the models from scratch, and it's like I said, it's not a lot. Like just like I said, this creating the fountain was kind of like trial and error. I plot out the points, I just render out the points only. Then once I have all the points, I do a lathe. So I really don't want to spend too much time in how those models are created because, like I said, they're kind of rinse and repeat of road and everything else. The only other main function I did was P placement. What this P placement does, it's a modified version of look rotation from quaternions. So this thing kind of creates a quaternion for me. A normal look rotation is you pass in the forward vector that you want your model to be looking at, like what your forward vector is, and then you kind of pass in the world up vector. And the look rotation within, it's kind of commented out, but it calculates the left or the right, whatever direction. So you have the left, the forward, and you have your left. And then by using the forward and left, it recalculates a new up. Because if you're at a new angle, up is going to be at a different angle. So based on up and your forward direction. But I can't use look rotation because I want to place all the objects on the sphere. So I need the up to always be the actual up. So I just, like I said, I took the look rotation and built a new function. And the only really difference is I'm not passing the forward position. I'm just passing up the up position that I want. And placing a sphere is pretty easy because you got to remember a sphere is a center point plus a radius. So all I need is a vector between a center point and some radius direction. So the planet is built like a grid. So if I say, I want, let's say, x by 2 and then, y by 1, whatever. I create a direction vector from the center. Let's say it creates a direction vector that kind of points right here at this direction. So that direction will be I want to use that as my up direction. Because like I said, a sphere, its up direction is basically the normal of every point. That's the up direction of every vertex. So knowing that the up vector is the normal on the sphere, so I want to keep up. Up is the value I need to keep. It's not the value I kind of use as a starting point to calculate angles. Up will always be that up needs to stay up. So what I did is I take the up that I want to keep, and I created the world space up. And using those, I used that to create the forward direction. Like I said, the original function, you pass in the forward and the world up. This time, I'm just passing up the actual up I want to have, and then using the world's up direction to calculate the forward direction. Once I have the forward direction and the up direction, I create the left direction. So once I have up, left, and right, up, forward, and left, I have basically my rotation matrix. Because like I said, rotation matrix is really just the 3 directions that you're pointing. You just need the normalized vector of that direction. And once you have that matrix information, then you can kind of just keep the rest of the function, which converts it into a quaternion. Then I use that quaternion to, I use that to, with something else, I forget, with the translation. So this way I have the rotation, and then I have the actual position I need to be. And the actual position is that up direction, which should be normalized, times a radius. So that's really how I did placement for the planet. So like I said, this creates that rotation. So like everything was kind of just up on the origin, and by just using that function, I was able to very easily place these at the right orientation based on the planet. So it makes things very, very easy. So that function you might want to keep around, or just understand. If you just understand the idea of how look rotation works, you can always rewrite it to do different type of orientations. Like I said, this one I built it to have like a sphere orientation of up. That's probably what it should have called it, or not, because really this is like up placement, I guess. Like up is where it's always going to be, and you don't have a forward direction. So I think that's pretty much it that's in this file. So I'll just go into the HTML page, and I'll just show you how to create new materials. So notice I updated my low poly so I can pass in a color, and I have 2 shaders because I'll explain it why in a little later. But I have 2 shaders, but they're almost identical. I have the low poly shader that can pass in an array of colors, and I have the low poly 1C, which is 1 color, because I can only pass in 1 color. But yeah, it's the same as before. The only addition is that I can do set uniforms. You pass in the uniform name, and then the data that goes into it. And like I said, it's argument listed, so I can just keep adding key value pairs just nonstop, and it just generates my entire uniform list that can get loaded into my shader. So yeah, now this is kind of useful. So this way we can kind of stop being hard coding our shaders all the time. I'm probably still going to do that a lot for prototyping, but once we start creating scenes and using a lot of shaders, this would help a lot. So yeah, that's pretty much it. And the way I use placement, so yeah, like I said, I would get a spot, like a vector direction, basically. Then I will normalize it. That gives me the vector, normalized direction vector. And then I say I multiply it by 4. So that gives me the actual placement. And then I use position as the up direction. And I pass in the out variable is the rotation. So this is the contortion that gets updated. So once I have the position, which is the exact position from the center of the sphere, I guess I'm not passing it a normalized. I guess you don't really need it to be normalized. When you're actually doing it, when you're actually doing the mathematics. So like I said, it's that direction normalized times the distance of the planet. That's really the position, how you position it on a sphere. I remember someone was asking me, a YouTuber was commenting like, how do we do placement on a sphere? This is pretty much a nice function. Sorry, I forget your name. And I know you gave me I forget your name. Sorry. But I forget. Sorry. Yeah. So whatever. If you're watching, I remember you in the comments you asked about placement. That was one of your questions. I don't know if I explained it, but now there's some code of how to do placement on a sphere. I know your question was actually general about putting a bunch of grass all over the place, but you mentioned either on a terrain or a sphere, like king size planet. But for king size planet, this is how you put placement on a sphere. Figure out a point, use its radius, and then use a function like this to set up your rotation of your object on the screen. And that's, for the most part, that's it. Oh, yeah, now I remember what I want to say. The person who asked me that question also gave me Patreon, so I want to say thank you very much. Sorry I forgot your name, but I really appreciate your patronage. Thank you. And I hope your project worked out really well. I really do. I'm all about everyone learning this stuff. That's why I'm doing this. And as long as you're having fun and you're learning, I'm happy. And all right, so let's just go through the shader. Like I said, there's not much to it. The only big difference is I'm passing in a uniform, vec3, and this one I can do up to an array of 3. And by using the W component of my vector, I just grab that index color and use that as my color value. This part I don't need. This was actually me trying to fix something, and I kind of gave up and I changed it. But that doesn't need to happen. That you comment this line out. I just forgot to take it out. This is good enough for what you need. And this is the same thing. The only difference is, where's color? Wait, that's weird. 1C. Don't they have color in here? Uniform. That's weird. Oh, that's right, because the one color, it actually exists in the fragment shader in this case, I believe. Uniform, U color. Yep. Yeah, there's no point in if I'm passing in a color to pass it into, if I'm only passing one color, if I'm going to pass it into the vertex shader, that means I would then have to set up another variable that passes a varying to fragment shader. So in this instance, if I'm only passing in one color, saving a bunch of, doing varying from the same color to the same color is a waste of GPU time. So I just passed in the single color right into here. The only reason why I have 2 different ones is because certain models were designed with 4 components, and some models were built with only with 3 components. And I didn't feel like redoing some of the models, like the tutorial wise, and adding the 4th component so I can have everyone share the same shader. I decided just to make 2 shaders. So I think the road can only handle like 1, I think, and the planet's the same way. I just didn't want to add the 4th component, and I have to go back and change the code to handle it. So that's why I have 2 shaders, is because some models were built differently from each other. And that is it. That's all the code for king size planet. and there it is, all put together. You know, you can do more trees. If you want, you can always just create random vectors and then randomly add the trees to anywhere on the planet. I know the guy who I was mentioning earlier, one of the questions he has asked about how to put a bunch of, I guess, trees or grass all over the planet, but still avoid the roads. To me, I'm not exactly sure. You kind of would, I guess, create like a collider, essentially. So ideally, like trying to think, like if you can create like a square collider and then shape it where the road is, and a cube collider, I guess, a rectangle collider, would then be more useful. So this way you can use collisions, like find a point collision to square, and if that point exists anywhere in that square, you don't want to use it. That's one way I think you can go about making sure that you don't place it in certain spots. So, like I said, like if you put if you kind of just create an object that's basically like a square collider on every single object, and then every time you do a random placement, you just check those 4 pieces. Do they collide? If they do not collide, then the placement is good. And that's about it. That's answering that question. If you're gonna want to just randomly place them, but I don't have any collider functionality yet. That's why I'm not doing it. Else I probably would do. I just do random. Just check 4 colliders every time I add a new object. So that's all. This is King Sky's Planet. This is the end of the I guess second or third milestone in this series. I love the fact that this was all built mathematically. So if you follow along and you understand a lot of what has happened to create this, and if you just look at the source code and just kind of finish up on your own how to build a planet. Like I said, we did the road, we did the planet, we did the trees. All I did was change the settings, like the width, height, and whatever the road, so this way it fits better on the planet. I changed the radius of the planet, and then all I did was create these 3 models. If you don't care about these 3 models, then just change it. Just get the new settings from GitHub for the road and the planet, and then use the trees, and just if you want to just see the code where I kind of just loop them. I just make like 5 trees and just randomly loop them. They're not random. I have like an array of positions, I believe. I think that's how it works. I think that's how I cheated. Yeah. So that's all I did. I just had a list of positions, and I just end up looping and just kept creating trees. So ideally, you can do the same thing and just do random position, just random X, Y, Z positions, and then you just dynamically create models based on that position, and it would actually orient it because it'll use that rotation. And I scaled the tree because the tree is huge, so I did some scaling, which is no big deal. That's all built in already. We've already done all that. So yeah, I'm pretty happy. Hopefully, if you're doing this along, hopefully you're happy that you learned a lot of math. I learned about this whole milestone was really geared toward learning a lot about procedurally generated content in a way. You got to, like I said, all this stuff was not generated at all with a 3D modeling tool. This was all done mathematically. This is all done with just vertices and a lot of functionality. So, No Man's Sky, that big, well-known procedurally generated universe, starts off like this. You start off small and simple, and then eventually you gradually get bigger and better. Every planet starts with a sphere. It won't be this type of sphere. It would be more of a normalized cube that generates the sphere. Like I said, there's more than one way to create a sphere. So yeah, there you go. That's the end of this milestone. The next milestone is going to be bone animation. I already started prototyping, and I already got a finger bending, so that's kind of neat. So I already have some building a small framework and everything else. I did want to talk about this a little bit. I forgot to mention that in hindsight, the way I went about this was a very masochistic way. We did everything in raw arrays. Everything was done in raw arrays. Every function was built around using raw arrays, and that makes it very difficult to manage the data. Very difficult. That's one of the reasons why I had problems with certain models being 3 components and certain models being 4 components, because changing that one value from 3 to 4 components requires you to do a lot of changes to every function. And some functions were built for 3 and some functions were built for 4. It was a big mess. So the way I did it was really kind of a learning experience, because you learn how to do it the hard way. That is the hard way to approach it. Like, if you can manage all this data in flat arrays, like if you can do this all just fine with flat arrays, you're doing an awesome job, because that means you're learning really just how to manage lots and lots of data, very raw data. I see the distance a little off right there. But so yeah, in hindsight, with what I'm building now with skeletons, I'm building a geometry class that every vertice is an object, and every vertice is actually an array that's part of a point object. So this way, when we start in future lessons, we're going to do more procedurally generated meshes. But instead of doing the masochistic way of using flat arrays, we're going to use objects. And so the idea was to have a geometry class having an array of points, and each point actually holds that one vertex worth information. So it'll have our vectors, our vector point, which would be x, y, z, and it'd be dynamic to the point where I can add the 4th component. So if I create a model with 3, and then to decide I want to add a 4th component because I want to start coloring the vertices dynamically, that will be very quick and easy, and it won't ruin anything. So like I said, we did this the long, hard way to see how it all handles, how that all works, and then in hindsight, we're going to then build a framework that properly manages all the data. So since we know how to do it the hard way, now we have to take all that knowledge and make it the easy way. That's how I program. I always do it the hard way, and then I kind of come up with the easy way of doing it. So, and I know the easy way was always to kind of create, vector objects, arrays of vector objects. But like I said, in hindsight, I don't want an array of vector objects. I want an array of point objects, and each point object I want to be able to save all the data that represents that one vector. So in that one vector, I want to save a UV, the UV values. That one, I also want to save the normals. I want to save the bone weight. I want to save the bone index. Like there's a lot of data you can store just for one vertex, and a lot of the ways people do it is they just create arrays of, like let's say for vertex and for vertex and for UVs, they would basically create 2 arrays, one array of vector 3s and one array of vector 2s. Seeing how I did this, I don't want that. I don't want to create a bunch of arrays. Like if I want to create things dynamically and I want to create vertices dynamically, that means if I have to create a vertex and then I have to create UV, I have to be separate arrays. And if I want to delete them, I have to delete them separately. So I kind of have to manage them always together at the same index. That's kind of I think that's kind of a pain in the ass in the long run. So in the next lesson where I'm going to start doing bone animations, I'm going to show you how to do it where we store everything as a point object, and the point object stores all that. Our vertex, our UVs, our normals, bones, everything. So everything that's related to that one vertex in 3D space, that's where all the information is stored in that one object. And then you have an array of those points. And then you just have a function that we call flatten. And it kind of just, let's say, you just flattens the entire point into a big, huge float array that we can then put into our buffer. So that, in hindsight, is how all this should be done to make it easier for you as a developer, and to really just make it more flexible to kind of change things during your workflow. Like I said, when I was doing this, it was hard to change because I was using flat arrays. I wasn't doing it the smart way. I was just doing it the hard way. So, like I said, hopefully you don't feel bad doing it the hard way. But like I said, this is a learning process. We're always going to do things the hard way and then do it the easy way. That's why we're doing the fungi framework. We start the hard way, and then we slowly build up fungi to facilitate the easy way of getting around OpenGL or WebGL and creating all this fun stuff. So yeah, that's, I guess, enough babble about what the next stuff is. But yeah, now we're done with this milestone. The next milestone is going to be bone animations. I'm going to start off small, just having a bunch of just one simple model that we can kind of just animate with maybe 2 or 3 bones, and then eventually upgrade to a full model that maybe we can apply poses to, and then then eventually have that full model actually like load in an animation and have like a walking animation. And what I really would love to do is to get to a point where I have you can transition between maybe 3 animations. So you can have like a slider where the person in real time will go from standing still to walking to running. That will be, I guess, the end of the milestone to 3D animation, like a drone animation. I might do other things like morph targets. I like the idea of doing morph targets. So maybe I might end up doing that in that milestone, so we can do morph targets as well with our meshes. And soft body physics would be kind of fun to do. We'll see about that one, though. That's more complicated. But the most important thing is to get to the point where we can load in a 3D model and have it walk and stand and run. That's the end of the next milestone. So the next couple of videos is going to be focused on that. So if you like it, stick around, because we're going to get a little bit more complicated. Yeah, it's going to be a lot more math. Bones require a lot more math. It took me a while to get this little thing working. So that's it. Like and subscribe. Have any comments, questions, need help on a project? If you're doing this stuff for school, ask away. I'll help as much as I can. And see you guys at the next lesson.